He was distracted. It's not my fault. It's his fault. We're gonna try to do some tours like we did last time. We used to do it like every week, and that's a little bit too much. But a couple of them, there's been some options to do some tours of some job sites, or I think we can get a tour of the SIP panel factory out in like Belgrade, right? Were you talking about it? Someone was talking. You have a suggestion on a location for a tour.
One of the Main Street construction sites, RPA is doing the design on it. There should be steel fabrication stuff going on late October.
Okay. What day would work for that? Was Fridays work for you guys? Friday afternoons?
Well, y'all have class.
Yeah, how important is
What's
it
that?
we
Oh.
go to Kirsten's advanced?
Oh yeah, but we can go after that because that's just 12 to 1, right? So we could go like afternoons, right?
That'd work.
Oh, you do. You have it every afternoon.
Same
though.
too.
I have it on Monday. I have it for Monday, but
Mondays. Okay. We'll keep.
Actually, no, I have a Monday morning.
You have a Monday morning. Yeah, I have Monday morning. I have Monday, Wednesday, Friday mornings. So we'll maybe tentatively do Fridays, but unfortunately, Axel, do you have Friday?
I'm free. Yeah, I'm free.
You're free, and you have Friday afternoons in the MLC.
Till closing. Fridays at 6.
Just close it early.
Yeah, it's goes. We'll come up with something. We'll come up with something.
Just leave the answer scripted in there.
Yeah. Unavailable.
Should call it good.
Yeah, we'll
Just put like a WebEx
Yeah.
login on the tables.
right because I think Wednesday like afternoon you probably have hours. You have hours too, right? So all Wednesday, Thursday, Friday. You're yeah. So I don't think there's any good time. So we might just have to ditch some of you. Well, but Tuesdays, Thursday afternoons, you're busy. What about Tuesdays and Thursdays in general? Just like earlier on Thursdays?
Capstone till
Oh, when is this? Oh, the Structures 2 lab is on Tuesdays. You have what on?
Capstone
When?
noon.
Noon.
On Thursdays.
I'm also working.
Oh,
I
yeah.
also work on Tuesdays.
All right, well, someone's getting ditched, I guess, right? Maybe we'll send out a
You can do Saturdays.
Saturdays. I'm busy on Saturdays. Okay. So we talked briefly last time about, the history of it, and then this idea between the difference between pre-tensioning and post-tensioning, right? With pre-tensioning, you stretch the steel first, you cast concrete around it, then you cut it afterwards and transfer the load in. Post-tensioning, you cast your concrete with a duct in it, and then you have, cables that have plastic sheathing so it doesn't bond to the concrete, and then you pull it afterwards, and then you transfer the load, and you have these anchor points, right? And we briefly talked about that. Okay, and then we actually talked a little bit about a couple of pages from now. We talked about the steel properties and things like that. So let's dive into advantages and disadvantages. Somewhere here, I got my notes. Oh, it's hot in here. Oh my God, it's so hot, but I can't open that door or that window.
Class outside.
Yeah. All right, pros. All right, it's lighter. Obviously, I got one written in there already. Lighter, right? You get thinner elements, right? Lighter and thinner. You can get away with that. Improved deflections. Right, that pre-stressing helps us with our deflections. We'll talk about that later on in the semester. And obviously, I mentioned this last time. One of the main things is improved crack control. Right, which is usually, right, it's just like an aesthetics things, right? Looks better. But there are some like practical reasons. And nobody wants to go to a building with a bunch of cracks, right? Oh, sorry, it looks better, right? Without cracks. Just mention that, right? Right? One of the reasons, right? It makes you feel uncomfortable. Hate typing with this. Fuck. Motherfucker. Uncomfortable. There we go. Right? You ever been in a building that you see a bunch of cracks and stuff?
The basement of this one?
Yeah, the basement of this. Makes me feel uncomfortable. It could be structurally fine, but still just no thank you. right? Freeze, right? If there's avenues for water to get in, you can have the freeze thaw resistance can go down. Water gets in and expands, it contracts and stuff like that. Corrosion can get in there. Is an issue. Okay. Another positive or another pro here beyond improved crack control. We do get improved shear capacity. Right. Shear, loss of shear capacity is associated with tension, right? You get those tension cracks at 45 degrees. Well, if you pre-compress everything, it helps with that. Ooh, that's an important one here. Reduced stress range. Reduced stress range under repeated loads. Okay, where this is an issue is in fatigue. Right? You have less fatigue issues with pre-stressing. Right? It's the range in which you stress something that is affected by fatigue. If you're going from 0 to the max, and it'll have less cycles that you can go through before it fatigues. But if you're just going through a smaller range, you can do more cycles before it fails. All right, those are all my pros that I have. Cons, it's got moved way down here. Where are my cons? How many cons though? Oh, I see what I did. It's because it kept just going down. Right. Major con is cost. More upfront costs. Maybe in the lifespan it's not, right? Because you have less maintenance costs, but at least initially upfront, it's going to cost you more to do that. Right? The other problem, this actually is a big deal around Montana, is contractor and design experience. We don't have a lot of contractors that say in Montana that can do post-tension floor construction. Right? It's a very specialty thing, and so a lot of times a contractor has to bring in somebody else from the outside, and even the design side of things is kind of new to our people too. Our people are us Montana. I mean, it is, right? It is like in your job office. This is a new thing, and some of your senior personnel may have never done a post-tension floor design on anything, and so like where are you going to learn that from, right? And so that is a big deal. So this is. You might be able to bring something to the table being able to do this when we're done. Can have brittle failure mechanisms. And we should obviously try to avoid brittle failure mechanisms, but this you can get that. When tendons snap, they're gone, right? They don't have like a yield. We'll look at those in a few minutes. The steel doesn't have a nice yield plateau with a strain hardening. It's just gone, okay? And then the other problem is you don't gain much in terms of ultimate moment capacity. Uh-oh. You'd think you would, right? Because you're pre-compressing everything, but you don't. You actually, what is going on? Yeah, you actually don't have much, and we'll get into that like way later in the semester. We'll calculate the moment capacity, but the moment capacity of a pre-tensioned member and a non-pre-tensioned member are very similar to each other, right? And so you don't get much in terms of like your ultimate load carrying capacity. Again, this is just a serviceability thing for the most part. Okay, all right, loading stages. I said before, we briefly discussed last time that. We briefly discussed what the equation was, right? That we have. It's just F over A plus my over I, right? That's all the equation is. The actual mechanics are super simple, and we should get to those by the end of today. The super simple. But what it gets complicated with is all these different loading stages. Okay, I'm not gonna. I used to talk a lot about it. I'm not gonna do that. I'm gonna say simple calcs. Or loading stages, I guess. And varying material strength. What up, Neil? Coming right from a workout into a nice hot room to sit in.
Just a shower for you guys.
Oh, you did? Hey, thanks. Very hot in here. Right, varying material strengths, right? Right. We have pre-stress losses. Right. Concrete gaining strength. Right. Initial loading. Service loading. Ultimate loads. Right. Just a little, just my thoughts on it, okay? We're gonna define these in more detail later on, right? Exactly what loading stages we're talking about and what material strengths you use and stuff like that. But just to set the stage, we'll just say that. Right? The simple calcs are complicated by all the loading stages and varying material strengths. We have pre-stress losses, concrete gaining strength, initial loads, surface loading versus surface loading and ultimate loads. Right? Everything's just changing. Okay, so now we'll do, everybody get that? You get that? Get that? Everybody get that? Get that? Kyle, get going, go. You got it? Got it? Got it? Got it? Got it? Everybody get it? You get it? You get it? All right. All right, let's go down to the materials. Right, you got to define a few things before we dive into the actual calculations. We kind of set the stage for it, right? So again, we talked about the forces and the tension, which amount to loss of compression concrete, 35 to 60 KSI. So we lose a lot of stresses due to pre-stress losses, right? And they come from elastic losses. We got creep that can happen. We have relaxation in the steel, and because of those things, we lose some of our pre-stressing, right? Regular steel, right, goes up to 50. We talked about the 50, 60 KSI. 36 is your basic, right? We can't be losing that much, right? It wouldn't help us at all, right? Why do that? So then our steel, right? We want very flexible steel, so a change in length causes less of a change in strength, right, or stress, right? And so we want flexible steel, we want high strength, we want it ductile, we want it fatigue resistance, we want good bond between the concrete and steel, especially in terms of pre-tensioning, right? Post-tensioning, we don't want that bond, but pre-tensioning, we do want that bond, and we want this low relaxation, okay? So what the actual stress-strain response is, it's worth visiting a little bit on these material side of things. Regular concrete will do, or regular steel will do this, right? It'll go up, hits a nice yield plateau, goes across for a little bit, and then it goes through strain hardening, right? And then it breaks over here someplace, right? That's conventional steel. Right? And then this, right? 36 to 60 KSI. Right, somewhere in there. That's where that you hit that initial yield plateau. When you talk about the yield strength of steel, that's what we're talking about. This initial yielding, right? When we talk the strength of steel, but really there is a strain hardening that happens afterwards that goes up to about 1.5 times what yield is. But we pretend that doesn't exist in regular design, right? We don't actually take into consideration it's kind of built into the conservatism in design. All right, but what pre-stressing tendons look like when you pull them is they are a little bit more flexible, just a little bit. So they're gonna be a little bit less like that. And then they just kind of go up like this and they go, and then they break up here someplace. All right, man, actually, that's not trying to scale. I should make that, should I make it even more? I should go like, Oh, but it's right? It's really high, right? There, we're looking at around 270, 250 to 270 KSI up here. But there is no clearly defined yield plateau. Goes all the way up to there. Okay. That being said, they still define a kind of like a yielding. They do put a spot in here where they call it FPY, even though it's not real. They call this right here, we'll call that FPY, right? And it's at a 1% offset. You look at a 1% strain and they go over and they call that what the yield stress is. It's not real though. It doesn't have a big real plateau. You may remember doing this in mechanics of materials where you did like a 1% offset and then you like look at you do the slope at the beginning. You see the slope at the beginning and then you go off 1% and you see where it crosses. Did you remember doing this at all? Talk about it. The materials class. You remember it, Neil?
Yeah.
Okay. Yeah, something like that. Are you lying or you? It doesn't matter. We don't really need it in this class, but I just wanted to point it. Just trying to tie it into some old stuff. Okay, so that's ultimately right. So what we trade, and this happens a lot of times in design, right? Is we're going to trade ductility for strength, right? And so it's the same material, same basic materials, but we'll talk about the process of how they get it up to 270 KSI. But when they do that processing to get it to 270 KSI, you lose ductility, right? And you're going to have some sort of, you do get a little bit of softening before it fails, but obviously not like this. It does down here. All right, so the different types of reinforcing, pre-stressing reinforcing you're going to see. There's rods and bars. Okay, these have external threads. Ooh. External threads. And these things have an FPU, the U being ultimate, of around 150 KSI. Right? Our EP, or elastic modulus, is equal to about 30,000 KSI. Right? And they're not used in the US much. These are rods and bars. We actually have these in our lab downstairs. So we use them sometimes when we test structural elements. If the floor in the structures lab downstairs, it has all those holes that are around to anchor stuff to the floor. The way we anchor stuff to the floor is by post-tensioning items to the floor. So we've got like a hollow core jack down there. So you go, the pile cap. Was anybody around for the pile cap? Were you around for the pile cap, Kira? Cash did for his research, did a bunch of testing of these big pile caps. Anybody around for that? Look, you guys are. You kind of remember, Tony? We had this pile caps that we anchored to the ground and pushed and pulled. But in order to make that work, we put a post-tensioning rod, we go up underneath the floor and put a nut on the underneath side. And you go up on the top of it, and we have this hollow core jack that we would then put a nut, and we put the I was like, if there's only some way I could draw it, right? So the floor is doing this, right? Uh-oh. Again, I guess this is tying it to our research. So then you'd have like this. Here's our pile cap that we tested. Look like this, right? And we needed it anchored to the floor. And so there's little ducts that would go through like this, and then we would have, the post-tensioning rod that's in pink here go through. And we put a nut on it down here, and then we do our hollow core jack. There's a little bridge. And then our jack would be right here. And then we would use that jack and we would pull on that post-tensioning rod. Okay? And how we would pull on it, there's a nut right here there's a nut right there. And then, so we would use this jack. We would actually push against that nut, which would then straighten, which would lengthen this thing out, right? This thing would get all stretched out. And then underneath it, we would take another nut. Once we pulled it out, we would put a nut right here and tighten that nut against the top of the concrete, and then we would release the load. And so then that nut would have this massive force that's pushing down on this thing to hold it in place. So anyways, that's one place that we used it. If you want, you can go down in the lab and you can actually see a post-tensioning rod down in the lab. They're pretty cool. It works really well. Because in that way, in what we were doing in these tests, where we had this big load frame and we were pushing and pulling on the up here on the top. So there's a big load frame over here, and we were pushing and pulling on the top of that thing. And if we didn't post tension it to the ground, this thing would be wiggling all over the place, right? And we wanted it to not move. And then the only way to get it to not move is to cause a big post tensioning force to hold it down in place. Anyways, that's the rods. We have them in our lab downstairs. There's also these wires. The wires don't really get used much. They're smooth wires. Smooth. Uh-oh. Uh-oh. Not used on their own anymore. They used to be used on their own sometimes, but they don't really get used on their own anymore. Where they do get used are within a strand. Right. These are 7-wire strands. Twisted together. Like a rope. I forgot to bring it today, but I have one in my office. I'll bring one in so you can see it. I'll look at a picture of one here in a second. EP in this case is, we said we wanted flexible. Well, this is all we can get. 28,500 KSI. Right. So slightly more flexible. Slightly more flexible, but not a lot. All right, the FPU in these guys are around 250 to 270. Right. Used exclusively. Now, oop. And then we're going to say C table for dimensions. Okay, so 7-wire strands twisted together. Right? They are a little bit flexible, and the reason they end up being a little bit more flexible is because they are twisted into like a rope, right? And when we pull on it, there's a little bit of motion between there's a little bit of twisting and untwisting that happens when you pull it. So it ends up being, as a unit, it ends up being slightly more flexible than conventional steel, right? Again, this is where we're getting the 250 to 270.
How do these strands compare to like the ones they use on suspended bridges? Like the cable, like on the Golden Gate Bridge, those cables.
Yeah, I have no idea. I would assume that's conventional steel, right? I would assume that's conventional steel that has like very ductile response and stuff like that. Yep. I'll ask ChatGPT later. Okay. And the reason I say CM for dimension, table for dimensions, we'll come back up to this stuff, is you can't, because they're, I mean, this is what they look like, right? They're strands like this. And this is a cross section of what it would look like, right? 7-wire strand, right? 1, 2, 3, 4, 5, 6, 7, right? I think that one's got a name. It's like the king strand. They just go straight down the middle. Well, I'll go ahead and say it like if you're a pre-stressing guy, you really throw these terms around. And so if you're ever talking about a king strand, it's the one in the middle, right? And all these guys are surrounded. So that's what a 7-wire strand looks like, right? If I'm trying to figure out what is like my effective area for calculating, the pre-stressing force and stuff, right? You can't, when they define these things, they talk about the diameter. What's the diameter of it? Well, you can't just take that diameter squared over 4 times pi and then tell me what the area is, because there's all these little holes and stuff in there, right? So you can't do that. You couldn't do that in regular steel either, right? You know, if it's like number 8, you can't just say, well, number 8's divided by 8, and then I'm going to do that, because things get weird, because it's the United States, right? And we do imperial units, and things don't make sense, right? And so this is one of those cases. So when we're looking for the area of steel later on, you're going to have to use this, right? So if it says I have a, you know, 1/2 inch diameter strand, right? And I need what my area is, my nominal area of steel for design, I have to look it up in this table, right? So a 1/2 inch strand has an effective cross-sectional area of 1/2 inch strand, 0.144 inches squared. And that, which is not 0.5 times 0.5 times pi divided by 4, right? So just keep that in mind. I always get it. Somebody does the homework and they're slightly off of what everybody else's answers are, and it's because that's what they did for the area of steel. You can't do that. You got to pull it out of this table. Okay. Yep. And then the difference here, there is also a difference between compacted, right, standard strand and compacted strand. I don't think this gets used very much, but you can order it compacted, where instead of just leaving it like this, they send it through another process where they squish it down to make it a little bit tighter. I don't think this happens very much. Usually it's just going to be a typical strand like this, right? Just going to show you, here's the rods or bars, right? Just look like big pieces of rebar, but then instead of just having, you know, deformations like lugs for bonding, they actually have, this is actually threaded, so that you can, you know, thread this component on. This is a big bearing plate that you would use, right? They have couplers for them and stuff like that. That's the pre-stressing bars or rods, right? Sometimes they really bundle these bars, right? So this is more of a post-tensioning application. They have a bunch of, you know, 1/2 inch diameter strands into one anchor. So this is a big anchor point, and then there's a bunch of different strands in here, which is made up of a bunch of different wires, right? So if you're doing post-tensioning design, right, you can imagine, right, because remember with post-tensioning, the way that pre-tensioning gets added, or the way that the post-tension or pre-stressing gets added to the concrete, is 2 big point loads on the end, right? So that's what's happening right here. Think of the point load that this is going to cause, right? Each one of these things is carrying, you know, 270 KSI, and then you have, you know, however many there are going around. Think about the massive millions and millions of pounds of force that are coming in at the end of your specimen. So part of the post-tensioning design is designing that anchor point location, right? That's going to be lots of steel included where that post-tensioning comes in. Here's a big post-tensioning jack. This is for pulling a bunch of these at the same time. That's what this jack is about, right? This is where I wouldn't stand anywhere near. Like I wouldn't want to be this guy right here, because you got millions of pounds. I mean, look at the size of that jack that's pulling on this thing, right? It's pulling this way, and there's a big anchor point right there. This is a really clear description of how they get up to 270 KSI. Years of copies has led to this, right? So you start out with the base material. This is how they get up to 270. Then they heat it, right? 1470 degrees Fahrenheit. Then they cold draw it, so they pull it through like a small little die here. They pull it through, and then they lengthen it like that, and then they do strands. And then afterwards, once they put it together and they twist it up into a strand, then they could do stress relieving, right? And by stress relieving, we'll talk about this later, but it reduces the amount of relaxation you get in your steel. Right, and so they'll define those things. You know, something you order and that has to do with your pre-stress losses calculation. Sometimes you'll have stress relieving, and then strain tempering is where they heat it again and then release it. And then, you know, obviously, you know, these will cost more to get these things like this. But just to show you that it is standard steel, but they have to go through a big process to get that up. And then by doing that process, they then lose your ductility. Right? That's why we don't have a very ductile response. Okay. 7 wire strands, got the materials down. Like I said, I meant to bring that, I forgot it. I'll bring it in next time. I've got one of these. I basically have this. I have an anchor point, and a pre-stressing strand in my office. Now in the lab, I got the rods. Okay, so what do we want properties of our concrete? Oh, I'm sweating. You guys don't mind if I lecture with my shirt off, do you? Is that okay? Is that okay with you guys? Is that fine? Yeah, walk around. I was like, sure, how's it going? It might get an HR call.
The new president walks in.
Yeah, the new president walks in and I'm standing with my shirt off. You don't understand, it's really hot. I'm a sweater and it's really hot. All right, our concrete. All right, we went hot. Oh, how'd that get so small? All right. High strength. Same idea. And in fact, there's a minimum requirement of 6 KSI. There's a minimum concrete strength of 6 KSI that you have to use. And that's actually dictated by ACI. But it's typically around 10 to 12 KSI. Because we want to put as much pre-stressing forces in there as we can, right? And obviously the strength of our concrete's gonna dictate some of that, right? We can't be stressing it more than 6 KSI. We want to get more and more in there. So usually it's 10 to 12 KSI. Especially nowadays, it's pretty easy to get a 10 to 12 KSI, right? We also, tied to that, we want high early strength, right? We want high early strength because we want to be able to transfer the load from the steel to the concrete as soon as possible, right? If imagine like a pre-stressing plant, you have to stress that steel first and then you cast concrete around it. Well, now you're taking up an actual bed at your plant, right? You're getting paid to make these things. And so you cast concrete around it, and I cannot cut the steel and transfer it into the concrete until the concrete's come to strength, right? And so you want something that gets high early strength, because if I get my high early strength, then I can come cut it, it'll transfer the load, then I can move it out of the way and put another one in there and make my next one, right? Or even on a job site when they're doing post-tensioning, you cast your concrete, you go in, you cast your concrete floor, and then you want to post-tension it, you want to post-tension it afterwards. I just realized you have a sweatshirt on, Sean. How are you doing that, right? Okay, you're post-tensioning afterwards. But I want to be able to post-tension it and then go on to the next floor, right? Well, I have to wait till the concrete comes to strength before I can post-tension. If I do that too early, you can crush your concrete and stuff like that. And this is tied to the loading stages we mentioned before, right? So high early strength is something we want. Actually, in those pre-stressing beds, they actually steam cure everything. Those beds have built into them the steam curing that happens. So they wait for the initial set, and then they have this heated steam to hit it with, so they can get your strength even faster. Okay, you want high stiffness, and we don't want it to deflect much. If it deflects a little bit, you get more pre-stress losses. Right. This is tied to aggregate stiffness. The stiffness of your concrete is tied to aggregate. So if you use stiffer aggregates, you get higher concrete stiffness. Right? We want low creep. Right? This is tied to low water cement ratio. Right? Good aggregates. Right? And low paste. That was a big one, right? We talked about that last time. The paste, it's kind of like a glacial flow. If you have a lot of paste in there, you get basically the concrete kind of flows. If you have low paste and more aggregates, you get less creep, right? We want low shrinkage, right? Same way, we're gonna go low paste, low water cement. Right? Shrinkage has to do with the drying out of the concrete. It'll shrink over time, right? And we don't want that. Because again, if my concrete shrinks or creeps, I lose pre-stressing when that happens. Right? Obviously, we want durable. The way we're doing this is, the reason we're doing this is to improve serviceability. Tied to that is durability. Right? And so there's going to be things floating around here. F prime C, we're going to see this, we'll define this a little bit later too, but F prime C is what we're used to seeing, right? That's the 28-day strength. But when referring to initial stuff, it's F prime CI is what it is. And that refers to early strength. Release. All right, and the I is for initial. But that's why we care about releasing. We need to know what the strength is at release. Right, and that's why a lot of job sites, they actually have these maturity meters hooked up to their concrete, so then they can kind of track what their concrete strength is going to be, and they know when to release things. Okay. There's our materials. Kind of set the stage for them. Basically high strength materials, high strength concrete, high strength steel. And you can't just grab conventional steel, you can't just grab conventional concrete.
Do you use like conventional additives in the concrete?
Yes. Yep. Just try to, whatever you could do to make that happen, right? So you go really low water cement ratios and then add in some water reducer to get a little bit more flow out of it and stuff, right? What's really nice is on, pre-stressing plants, it's a factory, right? So they can be really specific with their concrete mixes versus post-tensioning, right? It gets done in the field, right? And it can be a little bit more complicated. A perfect example would be our parking garage. They had major issues with our concrete in the parking garage because our parking garage is post-tensioned, and they had very specific, had to have a certain slump. It had to have corrosion resistance because you have the salts that get moved into it. It has fibers in it, has all sorts of stuff. Actually, one of the floors in the parking garage did not come to spec in terms of concrete, but everything else had been cast and everything by the time they know, and so they had to sharpen their pencils and do some calcs afterwards and stuff to make it work. You should ask Jay about that.
Oh, did you do that?
Yeah, they were doing that one. And I know there's some major issues with one of the floors, but they were able to calc it out and it still worked afterwards, even though it didn't make it happen. But it was very complicated mix that they had to use. All right, so reinforced concrete. This is just to kind of contrast regular reinforced concrete with pre-stressed concrete, right? So, and I mentioned this before, we start out with strength design, right? So in regular concrete, what you learn back at Structures 2 and what you probably learned, Tim's concrete class, the concrete was last semester. Those of you who took, right, the concrete, you always start with strength, right? And what you care about, right? And in fact, most designs start out with the moment capacity. We had to make sure that our MU was less than or equal to our phi MN, right? Our demand was less than our capacity. You then checked your shear, had to be less than or equal to your shear capacity, right? And then on the serviceability side, it's such a strange thing when they take like two words and they just put them together and they call them a new word, right? Serviceability. Right? But then sometimes they really fuck with you because then they make it like an ability as opposed to an ability. You know what I'm talking about, right? And if you know what I'm talking about. It gets me every time when they have an ability instead of an ability. All right, serviceability, right? And there we're talking about deflections, right? You came back and we checked our deflections. Right? After we made sure nobody would die, then we said, okay, well, does it work, right? So deflections, and this was tied to, really in regular concrete, this is the H-min that shows up. Right, there's an H-min. That's actually in Structures 2, that's all we did for serviceability checks, is we just said, hey, is my H less than H-min? Or, sorry, greater than H-min. Great, and then it works. Or you can calculate. Probably in Tim's class, you calculated deflections, and there was like the cracking moment and things like that you had or the cracking modulus, and you took that into consideration and stuff, right? So then you dive in. But the whole point there, start with strength, check serviceability. Pre-stressing, that's not the case, okay? We start out with serviceability. And that's why we're doing this, is for serviceability concerns, okay? And we'll look at it in a little bit, just a little foreshadowing. What it ultimately boils down to is making sure that our stresses are within a range. My stresses in my concrete, my Fs, we'll say absolute value because we're going to learn about signs in a little bit, has to be less than or equal to F allowable. Right? This counts for compression and tension. So that's why I put like the absolute values on the outside. Because again, we're gonna have signs associated with this shortly. Compression's gonna be negative, tension's gonna be positive. We just have to make sure that our tension stresses are not bigger than our allowable tension, and then we'll make sure that our compression stresses are not more than the allowable compression stresses, right? And so that, again, this is all elastic analysis, right? This is back to mechanics and materials stuff, right? Right? We're worried about cracking, right? And cracking is tied to this F allowable, right? There's an allowable amount of tension stress that can be in our concrete. If we get more tension stress than the allowable, then we're going to get cracking. It's all tied to cracking, right? And then also deflections is something we check first too, right? We're doing this for serviceability, and our deflections are more complicated than just an H-min. We're actually going to calculate the actual deflections we're going to see in our beam, okay? And then strength is an after. Oh, by the way, once I get it working for serviceability, then let's make sure that our strength works. We still do it. We still check the same things. Our MU has to be less than or equal to phi mn, and our VU has to be less than or equal to phi vn. Right? That still happens. We actually still have to make that happen, but it's after the fact. It's a secondary check, which always seems so weird to me, because your whole design career has been the other way around, right? People don't die, then we'll check to make sure that that it'll work serviceability wise. This is serviceability going to work? Oh, by the way, are people going to die? Obviously, if you find out people are going to die, then you have to redesign things. You don't get away with it, right? And the other thing that's floating around too, this is service loads because it's serviceability things. Unfactored loads are happening over here. When you go over here, factor your loads, right? This people aren't dying. This people are dying. People are dying, factor loads. People not dying, don't factor your loads. Use what you actually think it's going to be. Okay. Design philosophies. Okay, here we go. Starting to talk mechanics. Okay. These, again, I'm just following Stanton's notes, right? Your first assignment, I'm going to assign a homework here shortly. Okay? One of the first things is to read through Stanton's notes, chapters 1, 2, and 3, just so you can kind of familiarize yourself, plus some stuff out of the PCI design manual. But this comes out of his discussion, right? And we're going to talk about the moment curvature behavior, right? So how does moment relate to curvature? Curvature is kind of it's similar to a stress strain where you have a stress strain response, right? We plotted before, stress versus strain, right? Goes up and then it yields, and that's stress versus strain. But if we look at a section, what does a section do? Something equivalent to stress strain is a moment curvature. If I start bending a beam, how much it curves relate to how much moment it can carry? So it's just equivalent. Taking a step up where you stress strain is just just pulling on a piece of material or squishing a piece of material, whereas moment curvature is how does the cross section behave when I try to bend it? Okay, the cross section in that we're going to discuss here is this guy right here, a beam, right? A regular beam that has a pre-stressing strand that's off center, right? Previously, we showed a pre-stressing strand up here in our notes. We showed a pre-stressing strand being centered, right here, right? We showed it, well, that one's not really centered, right here. We showed it centered, right? But that's not the best place for it. The best place is to put it down where the tension's at, which is down at the bottom, right? And so that's what this is talking about. So if we start out, just kind of get us thinking in the pre-stressing world. So here it is. We have our pre-stressing strand off-center down at the bottom. So initially, and then what we're going to do is we're just going to start increasing the moment on it, this external moment. Right? I'm going to start increasing that moment, start bending it. And when I start bending it, its behavior is going to change, right? So starting out right out of the get-go, right, where I have no moment on it, right? My moment, where I'm not applying any external loads, okay? This thing is actually going to be curved up, right? So just because this thing is off center, we'll talk about it in a little bit. We'll actually write the equations down. But because that thing's off center, that has like two big point loads coming in right here. So the thing is actually, the beam without any load on it is actually going to be curved up. It's going to be bent upwards, okay? And that's why it has a negative curvature over here, right? That's why it starts off to the left, is because it's actually bent up. It's curved up. But as I start increasing the load on it, right? As my moment, right? This is my moments on this axis and curvatures on this axis. So this is a negative curvature when the moment is equal to 0 because it's bent up. But as I start increasing that moment on it, right? And say I just have the self weight on it, right? My stress distribution is going to look like this, right? I'm going to have a bunch of compression down at the bottom and less compression at the top but it is still gonna be a negative curvature, just under its own self-weight. It's gonna be bent up a little bit still. That's why we got a little bit of negative curvature under the self-weight. And so that's actually a little foreshadowing. When we look at release, when we talk about, you pre-stressed your steel, and you cast the concrete, and then you release it and you transfer the load into it, what we actually check is to make sure that we don't get compression failure at the bottom and tension failure at the top, which is opposite of what we usually think of, right? We usually think about regular reinforced concrete, I care about tension at the bottom and compression at the top. But under the initial conditions, when we first release the load, it's flipped. We care about, are we gonna get a compression failure at the bottom, then a tension failure at the top? And the materials we're talking about the concrete's weaker at that point at release, and so we have to consider one of the things. Anyways, so it's a negative curve. It's still curved up. If I keep increasing the moment, right, I can actually get to a point that's called a balance point, where my stress is uniformly distributed across the cross section. That's what I call a balanced condition, right? Is that my stress across the cross section is perfect, and I have no curvature in my beam at that point. It's just perfectly straight across. And actually, that's one of the design. This is actually when you're designing floors, you actually are aiming for this type of balanced condition. The reason you want that balanced condition is because if you imagine this thing over time, right? How is this thing going to creep? Like if you had a floor and this thing is a balanced condition, when it creeps, it's just going to be flat after it creeps, right? If you have this case, it's kind of weird. If you have this case where it's like this, it's going to cause the thing, it'll start creeping up over time. And so your floors in your building will actually have like a curvature up. But versus out over here, if I have something like this thing is actually, your floor is going to creep down as you go. So this is kind of a balanced condition is one of the things we aim for in design, is a balanced condition, because then if it does creep, it just stays flat as it goes. All right, and this will happen when your internal moments and your external moments cancel each other out, okay? And then we get to another point where it's called decompression, right? That decompression will happen where the extreme bottom fiber will get zero tension, right? Or zero compression. It'll just be way down here at the bottom, right? It starts out pre-compressed, but I'll add so much moment on it that I'll get to a point where it starts to become uncompressed, and that's the decompression point. We keep applying load, we'll start getting tension in the bottom, right? This tension, basically the external load will be so much that it starts canceling out what the pre-stressing is doing, right? And then you'll actually get to a point where you can crack it, right? And so and that'll happen when we hit FR down at the bottom, which is our rupture capacity of our concrete. And then we just keep applying load. Then it starts looking like what you're more used to seeing in concrete, where you have, the nonlinear stress distribution of your concrete, and now we're getting our steel is being stretched out to FPY. We just keep applying load, and then now we get the full nonlinear and the FPS. And so remember what we did in regular concrete. We went in and we put in a Whitney stress block, and we had a certain amount down here. We're going to do the same thing. Whitney stress block will come back in later on when we talk ultimate capacity. But right now, the initial stuff under the serviceability conditions, everything's linear elastic, and it's just those simple equations. But out here, then we'll have to do this. And so that's how we're going to teach it too, is I'm going to start out, let's talk about doing the design in the elastic range and how we do that in design for serviceability. And then, oh, by the way, boom, let's go out and check to make sure that, using Whitney stress block and everything else, our moment capacity is okay. Break. Right.